So I want to welcome everyone to this afternoon's webinar. We're going to be discussing the topic on the screen, maximizing lagoon energy efficiency. My name is Ben Shakman, and I'm the Midwest Regional Manager for Triple Point Environmental. I'm going to throw an agenda up here on the screen in a second. There we go. So just real briefly, what we're going to be talking about today, and I do want to point out that at the end of the presentation, I'm going to share a slide that shows our Lagoon University site, and there's some great options out there for PDHs and CEUs for those who need them. And of course, there will be questions and answer at the end, and just please use the functionality in our web-based platform to ask any questions that you may have. And at the end of the presentation, Eve will pull those together for us, and we'll talk about those too. I'm going to go ahead and make the camera make the camera go away in a second here, make the images on the screen a little bit bigger so that they can be seen better. Brief introduction of myself, your presenter this afternoon. I appreciate you taking the time to listen to me and engage in this conversation about energy efficiency for wastewater lagoons. And our marketing manager, Eve, has put together a nice handout for everyone. This is downloadable under handouts on the webinar menu. And the idea here is that there are going to be web links and resources all throughout this presentation. And rather than trying to copy them down as they show up on the screen, probably easier to have them available for you here. And of course, anything that you miss or want to hear more about, just please stick a question in the question bar and we'll dig in there too. Questions that cannot be answered while we're on the call today, we will get back to you via email. And looking a little bit at Triple Point and who we are, Inc. magazine named us one of the 5,000 fastest growing companies in the US a couple of years ago. They extended that honor to us again last year. We're very proud of that. We're also quite proud of the fact that their new regional program that they came up with in 2020, that was the first year. They recognized us in 2020 and again this year. We are the #2 environmental company on that list for the Midwest. Top 250 in the Midwest is that one. We think it probably has a whole lot to do with our installations and our project history. On the screen, you'll see a mixture of projects that go back to 2003, and they range in size flow, if you will. From 5,000 gallons a day up to 13 million gallons a day across the US into Canada and some other countries as well. And I'd also like to point out that any given year, we do about 50-50 revenue between municipal and industrial projects. But a lot of the industrials show up with non-disclosures. As such, they can't be on this list. We can't talk about them or show them in our videos or anything like that. The real list is a bit longer. These are the ones that we can discuss publicly. And thinking about the products that we offer, Aries is our lagoon aeration offering. Nitrox is for ammonia removal. If you have a need to denitrify, to get that third step of the nitrification process, we can add an anoxic zone and some mechanical mixing, and that's called Nitrox Plus D for denitrification. And our final product on the screen is Phosbox, and that's a lagoon phosphorus removal application. And that is about all of the company-specific stuff I have, so we're going to dive into the content now. Start with a little background, and I think that this is just a great slide that tells a really neat story. Hopefully I can get it to build here. Now, I apologize, for some reason this slide isn't working now. Were it working, what you would see is state by state popping up all of the lagoon installations, and they show up as pins. And by the time that the map is done building, it's completely full, and I apologize that that didn't work. We'll try it one more time here, and then we'll carry on. Okay, so according to the EPA, there are over 8,000 treatment ponds in the United States. Had the map worked, you would have seen that the US is just covered in pins for treatment ponds. Been in use for over 3,000 years. And I mean, talk about an old and proven technology. You dig a hole in the ground and you put your waste in it, and microbial organisms that naturally occur in the environment just chew their way through it. So out of that 8,000, more than half of them, I'm sorry, out of the all of the wastewater treatment plants in the US, more than half are lagoon systems. Earliest recorded one in the US is San Antonio 120 years ago. And I've got a couple of nice quotes here from the EPA. The first one, you're going to see some more on this. Ponds generally require less energy than other treatment systems, lower operation and maintenance costs, all good things. And then the other one down there, this is pretty staggering. Approximately $4 billion a year being spent on the energy to power water and wastewater treatment for the public. And I do need to point out that that was as of 2012, and the last 9 years, energy costs they've only increased. So just a really big amount of money that we're talking about as far as the energy that's consumed in treating our water here in the United States. There we go. So some fundamentals, according to the EPA, we're sticking with them again. Saving energy through these efficiency improvements can cost less than generating, transmitting, and distributing energy from power plants. Lots of economic and environmental benefits associated with doing that. Reduction of operating costs. I don't think there's a local government out there that wants to spend more. Reduction of operating costs is a giant benefit, and that frees up resources that can be used for other priorities within the municipality. And energy efficiency can also help reduce air pollution and greenhouse gas. Greenhouse gas emissions improve energy security, independence, and create jobs. And I feel pretty comfortable saying that we can agree these are all good things to do. They all benefit our communities. So looking at some background on the question now about energy efficiency, the American Council for an Energy Efficient Economy publishes a scorecard. They've been doing this for almost 15 years now, and they rank the states. We can see California #1 and most improved Nevada. Congrats to folks out there. But they assess performance and best practices and look for who's leading the charge, leading the industry as far as deploying energy efficiency strategies to support the climate goals of the state. They rank the states. So that's something out there as far as background. We're going to switch next and talk a little bit about energy consumption fundamentals. So first question, how do we reduce energy consumption in our plants? Answers, a few of them on the screen right there, not a complete or an exhaustive list, but starting with equipment upgrades and operational changes, those are big things that really, really move the needle. Modification to facility buildings, you'll see a smaller return on those, but they're still worth investigating, especially once you've got a mindset of we want to find a way to meet our permit, to treat our water, and spend less on energy. Definitely looking at the buildings as well is valuable. Quote on the screen here from the National Rural Water Association. We have a great amount of respect for NRWA and all of the state associations. You'll see and hear more about them in a few minutes here, but they want us to know their thoughts on the subject is that enhanced knowledge of the biology coupled with the innovations in equipment over the last couple of decades, it's resulted in some energy conservation opportunities that are easy to implement and often can be done with zero or very low capital investment. Also, they almost always pay for themselves and not that terribly much time. So all good stuff there, all good thoughts there. Continuing on these fundamentals, up top left, I want to point out the EPA. They're showing how energy is being consumed through a treatment plant and looking at all different pieces of the plant and assigning a percent to them. If you go over to top right, you'll see an example out of the University of Minnesota. They did some studying on electricity for activated sludge plants. And you can see aeration representing the lion's share of the cost there, the lion's share of the cost in the bottom left, lion's share of the cost in the top right for that, top left for that matter also. National Energy Laboratory, bottom left, and they're saying that you're going to spend about 78% of your energy budget on mechanical aeration. That is just a huge number, huge number. And I'm going to talk a little more on the chart on the bottom right. With everything that I've discussed previously and some of the guidance and some of the quotes, you'd really think that I would be able to have located and presented some data from within the United States that compares lagoons to other technologies. Unfortunately, I was not able to. And what I found out of the Journal of Applied Energy to share with you today to help make this point is actually data coming from South Africa. But interestingly enough, like we like to say at Triple Point, lagoons do it better. And if you look at that lagoon line, you'll see the electricity intensity. They're looking at the amount of power per cubic meter of water treated, lowest for lagoons amongst all of the technologies shown. Also, greenhouse gas emissions, those are lower than others. And really and truly, this helps support the point that Triple Point makes that for a city of less than about 10,000 people, certainly with an existing lagoon system, you're not going to get better results. You're not going to spend less money. You're not going to have an easier system to operate than that lagoon system. And quite frankly, it's going to be cheaper to do the upgrades to it and keep it in use for years and years, as opposed to replacing it or going in a different direction for treatment. Nice to see that proved out as far as the energy consumption as well. So continuing on energy consumption, 4 basic factors when you think about machinery and the energy they use is the electrical consumption, and what you pay for power is going to be important also. And then the specific power, and this is part of how we compare performance, generally expressed in terms of kilowatts required to create 100 cubic feet of air at whatever the discharge pressure is on the blower. And then time for wastewater treatment plants, lagoons especially, 24/7, 365 operation is most typical. And it's important to know that generally speaking, older equipment is going to be less energy efficient than newer. Our friends at Kaiser have a great example here. They've got a presentation out on the internet. You can download it and learn more about their equipment and the energy efficiency of it, but they provide this great example where they're showing a 100 horsepower load blower using as much electricity as a 75 horse screw blower. And for the larger blowers, screws and turbos you can see 20 or 30% reduction in your overall power consumed. It's very important to understand that screws and turbos are different machines than the positive displacement machines. They have different care and feeding, if you will, and different sweet spots. It's important to think about discharge pressure and depth of air release and things like that when evaluating what type of blower is going to be the best for the given application. Peak shaving, I want to offer a quick story here that comes from time I spent in the HVAC industry. I was involved in a project with a major financial services firm here in the St. Louis area, and one of their data centers, actually a campus full of data centers. And they discovered that they were paying their utility just about $50,000 a month in demand charges. And it was all about how the compressors in their chillers were cycling on and off. As we know, there's going to be an inrush current when you start a motor, and that's going to be higher. It takes more energy to get that motor moving, less energy to keep it moving once it's running. And this was completely a controls project. Simply by adjusting the sequence of operation and the ladder logic inside of their control system, we were able to do a project for, I think, if I remember right, it cost them about $80,000, which is like a month and a half of payback time. And then it's just pure return on investment beyond that. $50,000 a month these guys were spending, and we were able to get rid of that bill just by changing how their compressors turn on and off. Doubt there's going to be an example that extreme for a wastewater treatment plant, but if you look at your bill and you see demand charges, definitely you want to think about how you can stage equipment on and off in order to avoid being charged those. You're using the same amount of energy, you're just creating less stress for the utility, and they'll reward you by not assessing those demand charges. And then the bottom bullet there, the question, can load be varied seasonally or otherwise? If you take the approach of set it and forget it, and you never go look at your blowers, chances are that you're not running in the sweet spot. Chances are that you're either spending too much money pouring excess air into your system, or potentially not enough, and your treatment is suffering as a result. So think about load seasonally, think about it in terms of events. If you're a municipality that has a concert venue, you probably see spikes in your flow and loading around concert time. That would be when you want to ramp up your treatment. You know, if again, set it and forget it, chances are you're either suffering in terms of treatment or you're spending too much money on electricity. And a great way to spend less money on electricity is through the application of variable frequency drives. And a variable frequency drive, or a VFD, is simply a device that causes an AC motor to run at different speeds. They've been around since the 80s. And what they do is they drive that electric motor by varying the frequency and the voltage being supplied to it. That enables the operator to adjust the speed of a motor by changing either the hertz setting on a human-machine interface or directly on the drive itself. If your drives are tied into a SCADA system, you can probably ramp them up and down using SCADA. And a little bit later, when we get a little deeper in the presentation, I'll actually talk about an automated approach using DO control in the effluent. So VFDs, they're creating a simulated sine wave. Alternating current power shows up as a sine wave, and direct current power is chopped up. It looks completely different. You'll see that in a minute here. But just please understand that what a VFD is doing is creating a simulated sine wave. And I find this pretty interesting. The basic technology involved in these things has not really changed much since the 80s. The way that they work is the way that they work, and it's been that way for decades now. Very well understood devices. You've got three-phase 60 hertz power coming in the box. If you're looking at the diagram on the right side of the screen, your entry point is on the left, and you can see that it shows up as a sine wave. It lands on that diode block, and that converts it to direct current. Into the center of that diagram, you've got the capacitors. They're going to smooth out that DC, and they're going to create flat instead of sine waves. And then the third step is flowing over to the IGBTs, the insulated gate bipolar transistor blocks, and they chop the power into bursts of flat power as opposed to that sine wave. Those bursts of flat power of direct current actually alternate. That's how the drive is putting this out. They alternate, and they then appear to the motor as if they were alternating current. A technical term for that is pulse width modulation. And this is an interesting one that I wanted to share, a neat difference between one-phase and three-phase motors. If you look inside of a three-phase motor, the copper, the stator, the windings in there, they're actually powered separately by phase. A, B, and C each have a separate connection point and separate windings. I found that really interesting. I'll bring some more graphics in here to further illustrate my points on this slide. The converter, the DC bus, and the inverter, the big pieces inside of a VFD. And then there's a diagram that shows what that chopped voltage looks like. And that pulse width modulation, you can see there that you've got alternation with the DC voltage showing up as a sine wave. And that's what the motor sees. It's approximated. It's not absolutely smooth. It's choppy. But that's all that the motor needs to run. And this enables us to reduce and increase the speed of the motor using a variable frequency drive. But the way that they save energy is by allowing the operator to right-size the airflow to the treatment requirements. And that's interesting. I'm noticing that my graphics on this slide aren't playing either. I'll talk through those in a minute. So we can reduce the airflow by slowing down the motor that's inside of that blower, and slowing it reduces the energy consumed. And pretty simple here, less energy equals lower power bills. Over on the right, these are from engineeringmindset.com, neat little Neat little website, lots of graphics, lots of fun stuff. I will warn you though that you can lose like 8 hours of your life just by clicking onto their website because there's so much neat stuff there. But picture's worth 1,000 words, old saying there. On the top left, we see AC coming in, DC converted, and then it looks like AC. It's modified, it's a variable frequency, and the motor speed can now vary. And then the pulse width modulation, it's about the size of those pulses, how far apart they are and how wide they are. But that combined with switching the pulses is how they make it appear to the motor that the current is actually alternating when it's really direct current. Digging a little deeper on VFDs, the affinity laws tell us that power equals the cube of speed. And that's good to know, but that doesn't really tell the whole story. If you jump over to the chart on the right, you've got efficiency expressed as load a percent of the drive's rated output, and then variable drive horsepower on the far left. And if you take a look, you'll see that there's a relatively nonlinear relationship here. You've got some changes and some sweet spots, and it's important to understand that sizing of VFDs and sizing of motors, that needs to be done very deliberately. But you don't want to size for peak condition and then run in that condition, because you're probably going to be using a lot more energy than you need to. If your system's sized for peak day or peak hour, your average daily flow is going to be a good bit less than that, and it's important that you turn down your blowers to match your daily flow to avoid spending extra money on energy. But with retrofits, you cannot assume that you can automatically turn down a motor. It's really important to check with the manufacturers, both the drive and the motor, to ensure complete compatibility and make sure that you really can accomplish what you're trying to accomplish. It may be that the better bet is to leave that older that older blower as a single speed, just let it run constant speed exactly where it's set. And if that's a good bit over where you need to be, maybe you can resheave it and reduce your flow that way a little bit, maybe save a little energy there. And just an FYI, Lagoon blowers represent a constant torque load, and that torque is independent of their speed. The other type of load is a variable torque load, and an example of that would be a conveyor belt at a FedEx installation. I'll just pick on FedEx a little bit. As packages are put on and removed, the amount of weight that system is trying to transport is changing, and therein you have a variable torque load. Again, Lagoon blowers, constant torque load. So looking at what it costs to run a Lagoon blower and thinking about VFDs is my next slide here. And this example is one that we put together for a customer that wanted to model how their system would run and what it would cost to run. So over on the left, we've got a single blower in this model, and it's about 40 horsepower. 84% is all the utilization that's going to be required, so that's going to mean we're going to really be at about 33.77 on the brake horsepower with a 95% efficient motor. You can see the cost of energy there, and I'd like to also highlight the fact that the national average on industrial power is a good bit higher than that. These folks out in this example, I believe, is drawn from Montana. The folks out in Montana, I'm jealous. I'd love to be paying $0.0106 a kilowatt hour here in the Midwest, but even with our cheap power, we're not that cheap. So you can see hourly, daily, monthly there, and then a comparison with and without VFDs. And if you extrapolate that out, just using a straight line, no multipliers, no indices, no adjustments whatsoever, just simple math, you've got a 20-year savings of about $14,000. And a question to ask here is, what's it going to cost to put a VFD on that blower? If it was a $10,000 expense, would that make sense? Could that be approved? That's probably a bit of a long pull. But were their costs per kilowatt hour more like that national average or the commercial average? If you're on a commercial rate plan, you're going to be up over 10 cents a kilowatt hour. The more you pay for power, the bigger the savings get to look at variable frequency drives. But you shouldn't stop at VFDs. You should also consider your blowers. They are the biggest energy consumer at your wastewater treatment plant, and it's important to note that choosing the right blower is absolutely going to impact your cost of operation. So it's important that you understand your application in terms of flow and loading and detention time and stuff like that. If you're working with an engineer, they will help you determine that. If you're working with us or another firm in the industry, we're going to help figure that out for you as well. And you want to think CapEx, OpEx, but you don't want to stop there. You also want to think about service cost, and that last one there. You know, if I was presenting this webinar 2 years ago, it would have sounded completely different. But during these times, we all know that there's a transportation crunch, and availability of chips is down, and steel is up in price, and plastics are getting. It's a nightmare right now. And if you've got a blower and you're waiting for parts to be shipped in from somewhere outside of the United States, you're probably waiting a lot longer than you would have waited if it was a US built blower. So definitely ask those questions about parts availability, about service availability, about where is the technician that will show up to fix this if it needs something that's above my ability to maintain. Ask those difficult questions before you write the check on new blowers for sure. Understand and make people that you're talking to in government, city government, at the council, make them aware that payback can take decades. And also just understand that the most energy efficient blower out there, that might not be the best fit for you. You really and truly need to look at cost and serviceability, cost to operate it, cost to maintain it, and availability of parts. I think that 2020 and into 2021 is really driving that last point home hard. And to improve energy efficiency, you want to start with the blowers. That's your biggest payback, your biggest payoff, if you will. But please don't stop there. Think about everything you've got plugged in your facility. And if you look up and you see big fat fluorescent bulbs, understand that there's a lot of money to save there, and great programs exist for lighting and HVAC upgrades as well. Those are really the low-hanging fruit in most municipal and industrial applications, and the quickest, easiest, cheapest way to save money. But for a wastewater treatment plant where blowers are the biggest energy consumers, if all you're looking at is lighting and HVAC, you're missing out big time. So please consider every plug and every connection. Digging a little deeper on efficient blowers, the CAGI, where did my CAGI note go? CAGI, the Compressed Air and Gas Institute. According to those folks at the Compressed Air and Gas Institute, approximately 75% of a blower's total life cycle cost is going to be in energy. And isentropic efficiency is how we think about blower efficiency most typically. And I've got a little graphic here on isentropic efficiency. There we go. So that is looking at theoretical and actual power. And greater efficiency is going to yield a lower cost to run. But that comparison between theoretical and actual, theoretical is going to be a thermodynamic model. That's going to come from any number of government websites or guides that are widely available in the public domain, or from the manufacturer or whoever you're working with as a representative talking about blowers. They'll provide that data. But then real power is measured, and that's going to include everything other than everything else plus that motor. So that's going to be the blower, the motor, silencer, filters, drive losses. VFDs do consume some power. And then any auxiliary devices, if there's a cooling fan, an automated dampers, anything like that, and the controls to run the system. So real power looks at what it really takes to power that thing and make it run. Theoretical power is a little bit different. So thinking about efficient aeration, got a little quiz here. Which of these do you think is going to require less energy? Blowing air into the water or throwing water into the air? With any luck, my slide will work, and I've got some pictures. There they are. Give you just a second to think on this question. Blowing air into water or water into air? The answer is air into water. That fine bubble diffuser is producing just billions and billions of little tiny bubbles that are rising up to the surface and transferring oxygen into the water the whole time that they're rising. And it's important to note that those are fine bubbles. They're very, very small, and we can talk about how small they are. They're 0 to 3 millimeters in diameter, medium bubble and coarse bubble described as well. But take a look at that efficiency column. And looking at the standard oxygen transfer efficiency, or the SOT, it's measured in a percent per foot. So what percent of the oxygen can be transferred from the bubble to the water within that 12 inches of rise, that foot? And it's a by foot number. And if you take a look, you'll see that the smaller bubbles are transferring a significant amount more oxygen, significant amount. And if we think about a cubic foot of air, and we think about the bubbles that we can make with a cubic foot of air, we can make one real big bubble. It's going to have a surface area of 4.8 square feet. And that surface area, again, is where we're transferring air into the water, oxygen into the water. Looking at a medium, we're going to be about 185 square feet. A fine bubble is going to give us more like 1,800 square feet of surface area. And the efficiency of aeration is all about the amount of contact between the air and the water. So thinking about the rise time, thinking about the size of the bubble, and thinking about how much oxygen you're able to transfer to your water and how much energy you're expending to do it, we can graph this out and look at a comparison. Our Aries aerator combines fine bubble and coarse bubble, and this is looking at a 10-foot depth, and based on pounds of oxygen per horsepower hour. So for every horsepower that you run for an hour, how many pounds of oxygen are you getting into the air? And it's going to change depending on your airflow also. We've got fine bubble at the top, coarse bubble, and then surface aerators down below. And I'll take just a quick second and bang on surface aerators a minute here. And I've got some pictures coming up of some surface aerators, but we talked about the efficiency and throwing water into air being less efficient. If you're running surface aerators at your plant, and I've been out visiting a lot of plants that have surface aerators over the years. If you're looking at surface aerators, you probably have a graveyard on site, and you probably have a cannibalization pile on site. And you probably are no longer running the number of aerators that your system was designed to run. You've also probably accumulated some sludge in your ponds, and your treatment volume's been depressed as a result of that reduction in volume. So that says that you're putting less air into the water, you're treating for a shorter period of time, and basically you're just setting yourself up for the eventuality of not meeting permit. Surface aerators are inefficient devices. They still have an application every now and again, and they still are the right answer for very specific needs, but you really need to be willing to accept the higher energy costs. I'm thinking a little bit about these efficiency numbers here. I want to throw this up and be fully transparent. This is third-party independent verification of the claims that we make about our aerator efficiency. This is a full-scale production unit being tested. This isn't testing the components in fish tanks and then, through the miracle of math, determining what the efficiency is. No, this is full-scale testing by a third-party independent engineer, and validation on the screen there. So taking that for a spin a little bit, we've got the efficiencies that we've been talking and graphing a little bit. State-of-the-art oxygen transfer being the source for those numbers. I've got a surface aerator graveyard on the left there and one that's not running on the right, but looking at the center and thinking about how much air we're putting into the water. We know that different processes require different amounts of oxygen, and we generally think about oxygen and air in terms of dissolved oxygen, and we generally think about DO from the perspective of the residual. And that very simply is how much oxygen is left after the microbial process has consumed what it needs to support the bugs and to get the BOD or the ammonia eaten through, chewed through, and oxidized. But if you're running more DO than you need, if you set it and forget it, you just run your system full blast, even though your ADF may be a quarter of your peak, where that sizing was, look at how rapidly, and again, University of Minnesota doing some great research that I'm happy to be able to share here, publicly available. But I mean, look at that. Look at how much you can put a dollar value on each additional milligram of dissolved oxygen in your residual. What better way to make the point for running your system properly and efficiently? So thinking about the bugs and what they eat and what they do, we're going to talk next about efficient nitrification and some nutrient removal stuff. So nitrification, we know, is the process by which ammonia is converted to nitrites and then to nitrates. And this conversion is it's performed by a few of our little friends there. Nitrosomonas up front, Nitrobacter behind. Nitrosomonas is taking that first step from NH4 ammonia to the nitrite. Nitrobacter and Nitrospira helps us too on that, converting from NO2 to NO3 to the nitrate, excuse me. And then if there's a need to go to that final step, it's actually a heterotrophic bacteria operating in an anoxic environment, not a highly oxygenated environment, that performs that last step of the denitrification. But to nitrify ammonia, the amount of oxygen that's consumed when you compare it to lagoon treatment, when you compare it to the heterotrophs that chew through the BOD out in your ponds, think about it in terms of pounds of oxygen per day required to, pounds of oxygen required to oxidize a pound of stuff. A pound of biochemical oxygen demand, it's going to take between 1.5 pounds and 2 pounds of oxygen to support the microbial process that oxidizes that. The ammonia is a different constituent altogether. You're up at about 4.6 pounds per pound of ammonia. And with that, you see systems run at completely different DO levels. Quick little formula down there for the oxygen required, and a reminder here that the composition of air, only about 21% of the air that we breathe, this is at sea level, only about 21% of the air that we breathe is actually oxygen. So when you're thinking about how much air is required and you're at a higher elevation, it's really important to bring that fact up in the conversation, because the percent of oxygen does decrease as the altitude increases. Important to keep in mind. Also, those molecules are further spread out, more compression. That's a whole conversation all of its own, but just please understand that this is sea level, and if you're at a higher altitude, you need to be sure whoever you're talking to about blowers and airflow, they know what altitude you're at. You're going to operate the system at. So thinking some more about how much the biological community consumes, and ammonia removal via nitrification is going to use a good bit more O2 than aeration. That's because you've got different bugs. The autotrophs are smaller, slower, and weaker, and they're the ones that chew their way through the ammonia. But what they can't do is float freely in the water column. They've got to have something to attach themselves to. They're an attached growth organism. They don't compete very well, and as the temperature drops, their activity level drops. Heterotrophs, they do float freely in the water column, and they're doing completely different workforce, completely different organisms with completely different needs. They're doing the heavy lifting of the biological digestion. And I brought that graph from the University of Minnesota forward again because I really want to hammer this home, that providing excess oxygen results in extra expense. If you control your conditions, you're going to get controlled results. And that's really that's where the art and the science of wastewater treatment come together, I believe. So continuing to think about how we efficiently nitrify, how we efficiently remove ammonia from water. There's a way to do this. You can do this with automated control. And our nitrox, again, that's the ammonia removal system that we produce. You can see it in the bottom image there, but these are the basic components that go into setting up DO control. On the far right, you've got a sensor, and then the meter that reads everything is in the middle there, and a PLC over on the left, kind of a messy looking one, but they're not all installed beautifully. What you do is you set up the ladder logic and the PID control of that blower through a VFD such that you're reading your dissolved oxygen. And you're reading your dissolved oxygen in the effluent. And if you think back a couple of slides, you may remember I said that it's important that we have a residual because that says that we've provided enough to support the process we're trying to support. So if you're reading your residual on the back end of the system, instead of trying to read something in the tank, you're guaranteed that you're going to understand how much oxygen is left over after the biological process is completed. And that's where you want to read your DO with the nitrox removing ammonia in your system at the effluent. Then you ramp your blowers up and down using PID control and a VFD. And that's how you ensure that you're putting the right amount of air into the water, not the set it and forget it approach at all. A little bit more complicated. There's a little compressor that blows off that sensor, and there's a little bit of maintenance involved in that compressor. It's an annual rebuild kit. It's easy. It doesn't take long. It's an easy thing to do. But yeah, DO control on the effluent of an ammonia removal device will enable you to ramp your blowers up and down and ensure that you're properly meeting the needs of the microbial organisms that are doing the removal for you, oxidizing those nutrients. We're going to change gears now and jump into the case study stuff that I have together. And solar is up first. And before I start into solar advantages and disadvantages, just a quick diagram here. The sun is beating down on a solar panel and photovoltaic. I have such a hard time with this word, photovoltaic solar panel. Electric current is generated and it goes through a charge controller. Then out to a battery system. If you're powering DC devices, you can power them straight off of that battery system. For AC, you're going to run through an inverter. Same idea as that last stage of a VFD. And then you can power devices that way. And some advantages associated with solar. It's a renewable and inexhaustible source of energy. As long as the sun is shining on God's green earth, we're going to be able to run a solar system. There's no noise and no moving parts. And somehow Congress has not yet figured out how to tax our sunlight. Give them time. More space, you can fit more panels, you can generate more electricity. Flipping over and thinking disadvantages, it's got a high initial investment. We're going to hang some numbers on that in a couple slides here. The sun does not shine 24/7, 365, and batteries that are used to store that electricity, they require maintenance and periodic replacement. So you've got increased operating expense associated with it and increased capital expense to acquire the system. And I threw this one on here as a disadvantage also. If you've got a large demand in a small space to put in panels, it could be that you just don't have enough room to generate the amount of electricity that you need. And since this is a case study, we are going to talk about an actual system. So on your screen right now is a system over in Ohio. There's no power at this site, 2 cells, facultative. Average daily flow is a little over 250,000 gallons a day. And their loading is consistent with what 10-state standard says it should be. Couple of issues they asked for assistance with, the first one being odors. And aerating their facultative lagoons with Aries aerators is how we're going to solve that for them. And the second one is the ammonia exceedance and nitrox. We talked a little bit about that. That'll be our ammonia removal technology. So we gave an RFP to 2 different solar providers. We gave them the exact same information, the exact same blower spec, and I'll show that in a second here. They came up with 2 relatively different options. And that last bullet on the slide, I did a Google search as I was getting ready to put together this presentation because I wanted to understand other alternate sources of energy, and I wanted to know if wind was viable. Unfortunately, what I found was multiple lawsuits against people who installed windmills to power wastewater treatment plants, and as a result, wind was not further evaluated and won't actually be discussed anymore in this presentation. So let's jump in here. Let's look at these proposals. The first one, the first company to take a look at the plant in Ohio, they said you need solar and you need a battery and you also need a diesel generator. And their budgetary pricing was $350,000. They didn't really break that down at all. But their solution was an 84 kilowatt solar array. And knowing that land is kind of tight for the system that I just showed you, and there isn't a whole lot of ground available, we had a conversation about floating. But based on the cost of the accessories that they would need to add to the package in order to float their system, their quarter-acre system, it was just cost prohibitive and recommended against. So this is option number one. This is the first provider that we went out to. And I'm very deliberately not disclosing names here because I don't want to endorse any other party in the space or possibly dissuade anyone from not looking at somebody. So option number one there. Option number two, they developed the project quite a bit more, and their proposal was solar plus battery. There was no generator for them. Total was about $243,000, and they broke it down to show what the AC and the DC side costs, and you can see a significant amount of money in the storage capacity required for this. They came up with a 52 kilowatt array, and these guys love floating installations. They're all about floating solar, and they were a little bit smaller. Not a surprise given the fact that it's generating less power. A picture of their equipment there at the bottom. They also showed us what their equipment would look like at this plant, and that's what their 52 kilowatt floating solar plant would look like. Over on the right, a picture of their stuff actually deployed in the water. And if you find yourself on an airplane making the trip with children and grandchildren to see the mouse down in Orlando, look out the window as the plane's landing. And if you are near if you're on the side of the plane that faces their retention ponds at Orlando International Airport, you'll see a floating solar array there that's helping to provide power for the airport. US Army put one in down at Fort Bragg recently, and this is an idea that is really starting to take hold and grow, and it's starting to be deployed here in the United States. So additional thoughts on solar in Ohio. Two different companies looking at the exact same problem came up with two different solutions, 84 and 52 kilowatts in order to meet a little bit under a 15 kilowatt demand. When I reached out to an industry expert and I said, hey, what do you think here? Her answer was that the difference is likely due to differing interpretations of sunlight available. So I threw that website on there for everyone. If you want to go and look at the sunlight, your historical sunlight information for your location or any location in the US really, there's a website you can hit to go look at that. And while the capital costs are about $100,000 apart, if you think about it instead on a per kilowatt basis, they're very close in pricing. And unlike biological treatment requirements, solar isn't anything that the treatment manufacturers out there are really good at right now. So if you're thinking solar, you should understand that you're probably going to bring another party into the conversation, and you'll probably want a solar company to partner with in order to do a solar wastewater treatment plant. So ultimately, the city decided to spend the $50,000 that the utility proposed to run power, and this is going to be a conventional plant. My last bullet on this slide, this is my personal opinion, doesn't reflect the opinions of Triple Point, your sponsors, anybody else. It's just me. I believe very strongly that somewhere in the United States, somewhere we are going to have a completely off-grid solar-powered wastewater treatment plant. And I believe that that's going to happen in the next 10 years. I would love it to be a Triple Point plant. I won't put a marker on that though. I will say that somewhere in the United States, it will exist, a completely off-grid solar-powered wastewater treatment plant. I think we're probably within 10 years of that. Cost of storage being the real limiting factor at this point. So my next case study is a little bit different, and I want to talk about our friends at the Smart Energy Design Assistance Center at the University of Illinois. CDAC. CDAC is an applied research program, and it represents a public-private partnership between the state's EPA, an engineering firm, 360 Energy Group, some other entities at the university get roped in also. And their mission is to decrease the energy footprint in the state of Illinois. And I need to pause for just a second and say that I'm going to show some fantastic things that CDAC is doing for systems within the state of Illinois. But their mission is the state of Illinois. They're funding, their resource, their charter, it's all Illinois. If you're interested in what they're doing, look them up on the web. If you're outside of Illinois, reach out to your local university. See if your extension program can help you find a program like CDAC. I've got more resources coming up here also that will help you find other programs. CDAC is just so unique, and we're a company that's headquartered in Illinois that I asked them if I could include some of their information in this presentation, even though it's a national audience. So please understand that this is, I believe, a best practice, but it is localized in the state of Illinois. They focus on the public sector, treatment plants, state agencies, colleges, libraries, institutions. They're talking to building managers and owners, and they're doing these wonderful free energy audits that would cost you probably up to about $12,000 if you hired an engineer to do it for you. These folks have done a total of 90 assessments at this point in the last 3 years, and they've identified about $3.7 million in cost savings just in the state of Illinois. So the way that they get started before anyone shows up is they start with utility benchmarking and an overview, and they want to develop a really comprehensive understanding of your process. They want to know what problems you're having and what changes you think make sense. And they'll benchmark the energy consumption in your facility, and then they'll show up and do an assessment. They're going to walk through, they're going to look at your process, your equipment, your controls. They're going to ask you to run stuff. They're going to ask you to keep track of running hours and energy consumption where sub-metering is available. And they're going to do just a really, really deep dive to develop a robust understanding of your system so that they can then create a report. And their energy assessment report, a sample report off of their website on the screen on the left. Digging deeper on the right, you can see that they came up with four improvements recommended. Lighting and HVAC show up, and as you can see, smaller numbers there except for the HVAC. But automated DO control, we hit that one a little bit earlier. Variable frequency drives on pumps, a big topic in our conversation. And what they do is they figure out how you're running your equipment, how long you're running your equipment, how much energy it's going to consume, and how much can potentially be saved by making some changes. They present all of that data to you along with your payback in terms of the incentives that are available or just years to run. So in this case, looking at, they created package one, which focused on Vfds and lighting, and they projected out the savings there. You can see the project's estimated to cost about $34,000, potential incentives of $20,000. And CDAC, and there are lots of others out there that'll do this for you also. CDAC is all about finding every incentive that can possibly be applied to a project and putting in the work to help justify the savings, to help you get those rebates, help you get those grants, those incentives. Just fantastic work that they're doing. A little quick note here on this one, the majority of pumps already have variable frequency drives except for a couple of influent pumps. So the savings weren't as great on this one as they would be if they hadn't done an energy project, hadn't already added VFDs earlier on. So let's talk, instead of Illinois, let's talk about elsewhere, and let's look at how you can find a program in your state. Online research is a great way to go, and I do recommend that you look at case studies for similar plants. And if you find a plant that's running about the same kind of flow, that has about the same kind of equipment, it's going to be reasonable to assume that you're going to see similar, at least similar results if you do an energy audit and make some improvements to your plant. So it's a great way to kind of start thinking about how much money may potentially be saved. Resources, talk to your consulting engineer. The circuit rider from Rural Water Association, if you don't know him or her, that should be your best friend when you're running a wastewater treatment plant, especially a lagoon system. Rural water associations are fantastic. You'll hear a little bit more in a couple of slides on them as well. And of course, ask your utility provider. Ask them what benefits are out there, what they can do, what rebate programs exist. Ask them how much money they're going to throw your way and what you need to do to get it. Definitely touch base with your state university system too. I picked on the University of Illinois earlier. I've got NC State coming up. Lots of universities are doing lots of different things around the nation to help their constituents safe. And I do want to point out the custom program. I've got to believe that Ameren, Illinois is offering the most robust rebate anywhere in the United States. So when you think about and you research these rebate programs, you're going to see the very common industrial equipment listed with dollars per whatever, dollars per ton for HVAC. You'll see lighting. You'll see lots of very common stuff that doesn't really exist at a lagoon. But hopefully your state, or your utility, I should say, hopefully your utility provider has a custom program also. Ameren, Illinois rebates up to 19 cents per kilowatt hour for the first year's calculated avoidance. That is gigantic. That's the biggest check that I've found anywhere in the nation. Again, if you're working with Triple Point, we will help you find these programs. Another resource, American Council for an Energy Efficient Economy. They rank the states. They've got links to financial incentives on their website. I've got that address for you there, but I do need to point out that some of their links are broken. Some of that information is outdated. So please don't get frustrated. Just if you don't get something on the first one, keep looking, please. And regional programs, Midwest Assistance Program, I'm gonna call them out. Not for profit, they exist solely to help communities, small communities. That's their focus. They will help you define projects. They will help you identify programs to pay for projects, grants, loans, no interest, low interest loans. They are just experts at helping municipalities find money to fund projects on wastewater treatment plants. If you're in the Midwest, absolutely hit up Midwest Assistance Program. Great folks. National Rural Water Association. You've heard me call them out and sing their praises a couple of times. They're getting in the game. They have 25 states now where they have identified an energy efficiency, or I'm sorry, they have implemented an energy efficiency technical assistance program. They're hiring dedicated energy efficiency circuit riders, people, men and women who come out to your system at no charge and help you figure out how you can save money. They're in 25 states currently. With that program, they're across the nation. Again, if you're not linked up with your National Rural Water Association, please, right after this webinar finishes, Google them, join them. They're a great organization. They've identified over $11 million in savings through these audits. 1,500 assessments have been done. And I love this. 63%, about 63% of those assessments have yielded implementation. That is fantastic. Average savings of about $9,000 a year. You're not going to buy a new fire truck for your city with that, but I don't think there are many towns out there running lagoon systems that would say, keep it over $9,000 a year. I do need to point out that their Energy Efficiency Technical Assistance Program does prioritize impoverished communities. So you may have to wait a little while if you don't fit into that category. And then their link on the bottom of the screen, and that's in the handout as well. Another resource, Desire at North Carolina State University. I'm using their words here. They believe they're the most comprehensive source of information on incentives and policies that support renewables and energy efficiency in the United States. They've been around since the 90s, mid-90s, and they're at North Carolina State University. They get support from Energy Sage also, and there's their link for you. And my last big content slide here, the EPA's thoughts. They're a little bit dated. This is 11 years ago that this was published, but looking at what they say and the steps that they define, I think these are all still valid. I think that using this as a roadmap to thinking about energy efficiency is a great approach. They want you to develop a team, and that's going to be multifunctional, multidiscipline. You're going to have it's really going to depend on who's available and who you can convince to join the team. But ideally, you're going to have representatives of all of the different activities that have any stake in what you're doing. Probably some manufacturers, some vendors, some reps. You hopefully can get CDAC if you're in Illinois, or find a resource through the National Rural Water Associations or some of those other sources. Ask them to join your energy sustainability team. You're going to gather data, figure out some benchmarks, understand really what you're spending on energy, and then audit it. Figure out where you can spend less. Implement those improvements, and you want to monitor and measure. And then the last thing in there is to communicate success. If you've got a big win, please don't keep it to yourself. Tell the world. There's somebody else out there running a plant very similar to yours who would love to know what you did to reduce your energy costs so they can do it also. Spread the good news. So my conclusion is coming from the National Renewable Energy Laboratory, and working to understand the energy patterns and efficiency opportunities is a best practice that all communities can adopt. By tracking energy usage, benchmarking, and making operational improvements, all communities can begin their efforts to reduce energy use and realize some financial savings. I think that's a great thing to do. Toss the references up on the screen here. And next up is Lagoon University. So if you have a need to pick up some additional CEUs or PDHs, this is triple points answer. And we started this last year in response to the pandemic, when all of the shows and all of the training events were being shut down. We wanted to create content and have it available for free to support the industry. If you visit Lagoon University, click into the seminars, you'll find differing approvals. They do vary by state. But please, it's some great content. It's available for free. If you can get some CEUs or PDHs, all the better. If there's a subject there that can help you out with the problem that you're having, all the better, and they're free, and please help yourself. My Q&A slide is up now, and I love this picture, and it's a great reminder that yes, we're working with some objectionable stuff and things that the general public doesn't really want to be anywhere around, but we get to do the work that we do in some really beautiful picturesque settings. And I just wanted to call that out here real quick with the Q&A slide. And Eve, I think yes. That's the end of the presentation. Do we have questions?
I think we have time to sneak in one question. Why were windmills used as power for, well, it says lagoon aeration, but probably wastewater in general, targeted as a subject of lawsuits?
So that is a great question. And anytime that you install something at a customer's location, that customer has an expectation. Probably you're guaranteeing some level of performance. And in the instance of windmills, they would be generating, much like solar, generating an amount of electricity that's designed to meet the needs of that treatment plant, to power that treatment plant. I did dig in, I read through some of the lawsuit stuff, and what I found were allegations that sizing was incorrect, that the geography wasn't properly considered, that positioning on site was wrong or suboptimal, and it was just very interesting. Unfortunately, what I didn't find was an example to share of a wastewater treatment plant that is running successfully on wind power. If anyone has one, I'd love to know about it, but unfortunately, I was unable to locate one to share.
If you have time, I've got another one. I have an energy auditor on one of my plants today, but VFDs seem pointless if the operator is not monitoring DO. Is there a way to use these energy audits to fund sampling equipment?
So that's going to be one of those great it depends answers. And if you can draw, it's going to depend on your utility. It's going to depend on who's involved in pleading your case and how that application gets written up. But if you can draw a straight line between equipment purchase and energy conservation, and what that would probably sound like is that this sampling equipment is needed in order to verify the DO levels so that the VFDs can be manipulated to create the energy savings described in the attached blah, blah, blah. Probably it would sound something like that. And again, it's really, really going to depend on the utility and how well you make your case.
I think that'll wrap it up, Ben.
All righty. Thanks so much, everyone, for attending, and please have a wonderful day.